According to an airline, flights on a certain route are on time 80% of the time. Suppose 10 flights are randomly selected and the number of on-time flights is recorded. So we have several parts here. Part A, explain why this is a binomial experiment. So remember the conditions for binomial experiment. So we know you have to have independent trials. So make sure that's G. The probability of success is the same for each trial. So that's F. It's a fixed number of times. So there's D. And there's one more. Our success failure. We have two mutually exclusive outcomes. Okay, the probability that exactly 7 flights are on time. We're using the calculator for this or StatCrunch. Let's start with StatCrunch. So question help, StatCrunch. So I'm going to go to Stat, Calculators, Binomial. We have 10 is N, P is on time, 0.8, and we want exactly 7 flights, so equals 7. And there we are. So 7, it's about let's see, to 4 decimal places, so 0.2013. Let's check that on the calculator. And clear that out. We're going to go to second distribution, binom, PDF, because we're doing just one. So we have 10 trials. The probability of on time is 0.8. And our value here is going to be 7. 0.2013, exactly the same calculation. Now let's interpret this probability. In the 100 trials of this experiment, it is expected about how many to result in exactly 7 flights being on time. So we're just going to take that probability and multiply it by, sorry, in 100. I might have said 1,000, in 100. So that just shifts this point over 2 places and we get about 20 because it says rounded to the nearest whole number. So again, we got that by saying 0.2013 times 100. Okay, what about the probability of fewer than 7 flights? So on StatCrunch, I'm going to say less than 7. So notice the less than 7, we've got 6, 5, 4, and then the other ones just sort of peter out. We don't even get hardly anything for those. So less than 7 does not include 7. So I could say less than or equal to 6 is exactly the same computation, right? 0.1209, or I could say less than 7. 0.1209, exactly the same, right? So let me say less than or equal to 6 for the sake of this argument here, because we're getting ready to use the calculator. 0.1209, I'll put that in. Now let's use the calculator. So I'm going to go to second distribution. Now I could evaluate a bunch of binom PDFs, but I don't want to do that. I'm going to do CDF. CDF goes from 0 up to the certain value. So trials, we have 10. P was 0.8. And the X value, I'm going up to what? Not 7, right? I'm going up to 6. Because if I go to 7, that means I'm including that 7. So I want less than or equal to 6, which is the same as less than 7 when we have a discrete distribution. I'm going to remind you, see, there's my less than or equal to 6. I'm shading my 6 all the way down, and if I change that to less than 7, I will have exactly the same computation. Because less than 7 is, I don't include the 7. So that's why I say less than or equal to 6. It's one of the trickier things we'll do on the calculator with the binom. I wish it were easier. I wish it had an upper bound, lower bound, but it doesn't. We get exactly the same thing, 0.1209. Okay, in 100 trials of this experiment, it is expected to result in fewer than 7 flights being on time. So how many? Again, multiply 0.1209 by 100, and I'll get about 12. The probability that at least 7 flights are on time is what? So think about this. At least 7 means what? Means 7 or more. So at least 7 is 7 or higher, which is 0.8791. So make an observation here. Notice that at least 7 or higher is the exact opposite, the complement of less than 7, which is 6 or lower. So if I switch this over to less than 7, I get these highlighted. So it's 1 minus that. So with the calculator, I can just say 1 minus this value here. 1 minus second ands. Remember that ands brings up the last thing we did, and we get exactly the same thing. Tricky though. Very tricky. Notice I don't have the 7 in there. So make sure you kind of see what just happened with that. I'm wanting at least 7, so 7 or higher. So I found 6 or lower and subtracted it from 1. So again, in 100 trials of this experiment, it is expected about 88, if I round. 0.8791 times 100 is about 88. Ooh, long problem. Last one, I think. The probability that between 5 and 7 flights inclusive are on time is, so now we're evaluating what? 5, 6, or 7. So in StatCrunch, we can go to between and say, okay, everything in between 5 and 7. StatCrunch is crazy nice, isn't it? So it's just these values here, 5, 6, and 7, and it's about 0.3158. Let's see how to do this on the calculator. I would not recommend doing a CDF for this one. It gets a little tricky. I would just evaluate 3 PDFs. So second distribution, binom PDF, 10.8, and then we'll just start with 5. Get that one, and then press second enter and change it to 6. And then press second enter and change it to 7. And then we're going to add these 3 numbers up. 0.02642 plus 0.08808 plus 0.20133. And we should get the 0.3158 figure. There is a way to use the CDF, but I notice when students use it, when it's between 2 numbers, they always miss it. So I'm going to suggest you not use that and just do the PDF. It takes a couple extra keystrokes, but I think it's worth it. So hopefully getting the hang of this now. So in 100 trials of the experiment, it's expected that about 32 of the flights to result in between 5 and 7 flights being on time. Okay, long problem. Hope that helps.